Hello, welcome to everyone in this video. This is our lecture number 1 for the series of theoretical part of electronics. Today we want to discuss about the circuits and network. You can see this is the part of the syllabus: discrete component, active and passive component, ideal, constant voltage, constant current sources, network theorem like Thevenin theorem, Norton theorem, superposition theorem, reciprocity theorem, maximum power transfer theorem, and application to the DC circuit. This will be covered up in this lecture. Okay. So in this YouTube channel, you will be get the different physics related video with theoretical part and problem solution also. So if you want to watch these things, you can go through the description box. There are link are given in there, and there are separate playlist for each section. So you can go through the playlist of this channel. You will be get different part of the physics related video. So let's start today's discussion, that is this circuit and network theorem. Okay, you can see this is the syllabus for Calcutta University BSc 4th semester for the analog electronics. You can see that is the circuit network. In this network we want to discuss this part in this lectures, that is the discrete component, active and passive component, ideal, constant voltage and constant current sources, network theorem like Thevenin, Norton, superposition, reciprocity, maximum power transfer theorem. Clear? In the upcoming session, we will be discuss these things. That is semiconductor physics. Okay, semiconductor physics, PN junction, rectifier, bipolar junction, field effect transistor, regulated power supply, amplifier, feedback amplifier, operational amplifier, op-amp, and multivibrator, oscillator, etc. This will be covered up in the upcoming session. Right? Started. What do you mean by discrete component? Actually, discrete component, in the present situation there is a IC, integrated circuit, and the chips. These are be available in the present situation. But before that things, there is a discrete component like a resistor, like a inductor, like a capacitor. These are the discrete component. That's mean when this component of electronics are discrete, single device. These are the single device like diodes. This is also a single device. But in IC, or you can say in the IC integrated circuit, there is n number of diode, etc. combined, making a gate, right? So before that, these are the separate out, and the single device, this is the single device, is called a discrete component. Alternatively, now the IC and printed board circuit, PVC circuit, actually used nowadays. But before that, we actually use the single unit electronic device like inductor, resistor, capacitor, transistor, diode, fuse, switch. These also are the discrete component. Okay. These discrete components are broadly classified into two parts. Number one is the active component. Number two is the passive component. What do you understand by the active component? Actually, active component is the component that is positive power. Obviously, positive power, deliver the positive power to the external source, deliver the positive power. Suppose this is a device. This is a device which delivered the power. This delivered the power, positive power to external source. So when a component delivered the positive power to external source is known as the active component. Suppose voltage source and current source. This always supply the positive power to the external source. That's why this is called the active component. In the opposite sense, there are if the component cannot supply in the lifetime, there is an important thing is the infinite time period. So in the infinite time period, any device can supply the power, positive power, to the external source is called active component. But if it does not supply the positive power in the external source for infinite time, the main things is the positive power supplied to external source in infinite time is active component. If this does not happening this thing, that is, it cannot supply infinite number, or it cannot supply the it cannot supply positive power in infinite time, then it is called the passive component. For example, the inductor or capacitor, it can supply the power because when we supply the power in this inductor, it store energy and it can giving the feedback to the external sources. Similarly, for a capacitor, if you charge this capacitor and then is discharged, that means it's supplied to the external source, but it is does not okay in the infinite time, because it stored energy and it's decaying, so it is not an infinite. That's why the inductor capacitor also a passive component. I think clear. Two main things: when the device supply the power, positive power in external source in an infinite time, is called active, otherwise it is called passive. So voltage source, current source are the active component, and all other things like that is the passive component, because it cannot supply positive power to external source for a infinite time, that is a long time, right? Next portion goes in the linear and non-linear elements. What do you mean by linear element and the non-linear element? When the characteristics of IV curve is like that, which is passes through the origin, then this component is called the linear component. For example, resistor, this is a linear. But if this is not satisfy these things, you can say for diode like that. So this is a non-linear component. Diode, inductor, capacitor. You can see for capacitor charging, for discharging, like that. So charging, discharging. Okay. So for charging, discharging, so these are not valid for V equals to IR in all these region. Okay. So if throughout the region it's obey this relation, that is the this is the Ohm's law. This is the Ohm's law. If it satisfy the Ohm's law for a whole wide range, in the wide range, this is called linear elements like resistor. Otherwise, it is called non-linear for inductor, capacitor, diode, etc. Clear? Now comes into the point, that is the bilateral and unilateral. What do you mean by bilateral and unilateral? Bilateral means in the current flow voltage relation in the all directions, same in the all directions. Suppose this is a conductor. If you go through this current into that direction, the relation will be V equals to IR. If you flow in the opposite direction, they are also valid the V equals to IR. Then this is called bilateral. So it is independent on the direction of the current flow. So the voltage current relation, that is V equals to IR, is valid in each direction, is the same in the every direction. This is called the bilateral. And unilateral, suppose you have a diode. So when the current flow along forward, this will be the I equals to I0 exponential EV by eta kt minus 1, like that. But when in the forward, this becomes 0. Sorry, in reverse, this tends to 0, or it tends to I0, saturation current. Okay. So this is not the same in the opposite direction. That's why this is called unilateral. Unilateral means when you change the direction of the current flow, then relation between I and V will be changed. But when they are the same, this is called the bilateral. So I think clear about all this conventional notation, that is discrete component, that is not IC or PVC. These are two broad class: active component and passive component. In the active component, they it supply positive power for a long time, it cannot do that. In the linear and non-linear, linear is when V equals to I are valid for a wide range, linear, otherwise this is non-linear. Unilateral and bilateral, when this is independent in the direction of the current flow, this is bilateral. When this is depend, this is called unilateral. Clear? Comes to the next point. Next point is the ideal constant voltage source and ideal constant current source. What do you mean by voltage source? Voltage source means is supply voltage. When it is called ideal, when it is called ideal, it if the supply voltage is constant without with the change of the load current. If you enhance the load current and the voltage supply will be the same, then this is called ideal constant volt. Suppose that you have a voltage source. Suppose you have a voltage source. This is a voltage source is two terminal plus and minus. Okay. If you added a one load, its flow some current I1. If you added two load, its flow current I2. It's added 3 load, it flow I3 and so on. But the current is changes. But the voltage supply, the voltage at that point will be the same for any current value flowing to that one. Then this is called the ideal voltage source. I think clear? When if you added the load, the current will be changes the because the voltage is on. So with increasing current, the voltage will be the same. The load current does not affected the supply voltage. Then this is called the ideal constant voltage. So it is independent of the current through its terminal. So it does not depend how much current flow through this circuit. It's constant through for any amount of current flow through this. So if you sorted this one, the maximum current flow, then about the voltage will be constant. At that point you can see current is 0, then this is a constant value. If you tends to infinite current, when this is the short circuited, then also this will be the constant. This is the ideal constant voltage source. In the real life, if you enhance the load current, this will be fall down. For example, if you think if you think that in a ceremony program house there is a generator used, when the number of fans and light will be increases, then at a certain time this will be fall down. The curve will be like that, is versus vt. This will be constant at a certain level, but this will be fall down after a certain time, certain load. So for a certain load this will be constant, no problem, but after increasing the load this will be decay. This is the real voltage source, real voltage source. Okay, so this is the real voltage source. But in the ideal voltage source, this must be constant. This is does not affect with the external load current. Okay, now for real voltage source will be like that. The voltage difference at that point will be nothing but the Vs minus Is into R, the resistance, internal resistance of this source. Okay, because in real there will be a internal resistance within this voltage source, but in ideal this internal resistance of the voltage source must be 0. That's why the voltage always constant. There is no change with the external currents. Okay, so this is the ideal voltage source graph and this is the real voltage source curve. Go to the next one, that is the ideal constant current source. When the current source, when it supply the constant current throughout any change of the voltage. That means this is a constant current source. This is a constant current source. If you added one resistance, gives the same things. If you added two resistance, this is the give same things. Three resistance, you get the current will be same thing. So without changing the with increases the voltage on L things, the current of supply current is does not change. This is the ideal case, but in real case this is depend upon the voltage like that. You can see here IT is nothing but the IS is total minus this current. This current is nothing but Vs by R. Clear? So this is the practical current source and this is the ideal current source, and this is the notation of current source and this is the notation of the voltage source. These two are the notation of the voltage source. Okay, circuit symbol, you can see this is the circuit symbol of the voltage source and this is the circuit symbol of the current source. The same things. Next point, Next thing is the Kirchhoff's current law, KCL. This statement says that when the current flow in a junction, if you consider in a junction within a linear circuit means there is a voltage source and the resistor and the voltage source combination is the linear circuit. Okay, so in a linear circuit, if you consider a node, this point is known as node. If you consider a node point within a linear network circuit, then the total current within total current in this point must be 0, where the incoming current taken as positive and outgoing current taken as the negative. So current taken as the incoming current taken as the positive and outgoing current taken as the negative. Okay, then the incoming is positive and outgoing is negative, then what will be the value? So you can see the incoming I1, I2, I4 are the positive and the I3, I5, I6 are the negative. Total current must be 0. Okay, so this state you can see the I is dq dt, so dq is 0 means q is constant. That is Kirchhoff current law is nothing but the charge conservation. You can see this is you can say this is nothing but the charge conservation. Okay, so this is the Kirchhoff's current law. At the any load of a linear circuit, total inflow of current must be equal to the total outflow of current. That means the algebraic sum of the currents at any node must be 0, where the incoming taken as positive, outgoing taken as a negative. You can take the reverse one also, because if you this negative and this is positive, this must be 0, no problem. So incoming current, total incoming current must be equal to the total outgoing current according to the KCL, Kirchhoff current law. Clear? Next question, next portion says Kirchhoff voltage law. Kirchhoff voltage law means if you take a loop, this point is known as the node and this is a loop, loop in a linear network circuit. If you take a loop in the linear network circuit, total current into resistance must be equal to the total voltage source within that loop. So in a linear network circuit, total current into resistance, that is total current into resistance within a loop is must be equal to the total source within that loop. You can see here, if you take consider this loop where taking a resistance R1, current flowing I1, this is a voltage source, this is another resistance, this is a voltage source, this is voltage source, this is a resistance. Now consider this equation. You can take this clockwise direction as a positive, you can opposite that one also, no problem. If you take this as a positive things, if you take anti-clockwise as a positive, consider notation, you can notate that, and sorry, clockwise as a positive. So this is anti-clockwise, that's why this is minus I1 R1. This is also in the opposite, so that's why minus I2 R2, and this is the same, that's why I3 R3 is the positive. Okay, now comes into the voltage source. This voltage source, you can see this current is flowing from that voltage source in the opposite in our notation, that's why this is minus V1, and this is shall say this is the same, that is plus V2, and this is also same that's why this is V3. Okay, so this is minus V1, this is plus V2, this is plus V3. So this will be the Kirchhoff voltage law, KVL. You can say this is KVL. Kirchhoff voltage law will be like that. So this is nothing but the IR and this is VK. If you multiply the current, that is nothing but I square R, that is the power. This is the power, and this is the power lost through this resistor, and this is the power supply by the source. So you can say this is a power conservation, or in the other word you can say this is the energy conservation law. So KVL is nothing but the energy conservation law, because it stated that the total power used due to the resistor, total power used due to the resistor must be equal to the power supply by the source. So the power supply by the source is equal to the power used or dissipated through the resistor. So these two are equal, that's why the power conserved, or you can say energy sorry energy conservation. So KVL is nothing but the energy conservation law. Clear? Next point. Next one is Thevenin's theorem. This is the most beautiful theorem which you reduce your efforts or the calculation in network circuit. For example, you have this type of network. There is a combination of resistor and voltage source. This is a linear circuit. That means V equals to I are valid in the all component. That's why you use the resistor and the voltage source. In this resistor and voltage source, all these things can be replaced by a simple resistor with a voltage source in a series combination. This is the Thevenin theorem. All these component can be replaced by a simply voltage source with a series resistance. This voltage source known as Thevenin's voltage, and this resistance known as Thevenin resistance. Okay, if you consider these 2 points A and B, this is a point A, this is point B, all these things is replaced by simply that one. Okay, where VTH, what is the VTH? Actually VTH is the, if you remove this resistance RL and measure the voltage at this terminal using a multimeter, simply multimeter, or in a voltmeter. Using a voltmeter you just measure the voltage through this terminal, but just removing this the resistor. You can take this as a black box, no problem. Black box, within black box you have no idea how much amount of resistor or voltage source are available. Black box, if you take this as a black box, this black box can be replaced by a voltage source with a series resistance. The voltage is can be calculated by this multimeter or voltmeter at these two terminal. Okay, so at these two terminal you just using voltmeter using voltmeter. Okay, so using voltmeter you can just you can measure this voltage across this two terminal. And what will be the Thevenin resistance? Thevenin resistance is nothing but, if you just replace this voltage source using this internal resistance, replace the voltage source, replace voltage source, I think you are written here, equivalent resistance terminal, all energy source replaced by their internal resistance. Okay, so replace the voltage source by their internal resistance and measure this resistance. Okay, so you can easily replace this complicated circuit through a simple voltage with a series resistance. This is the beauty of the Thevenin theorem. I think you understand about the Thevenin theorem. This states that when a complicated circuit, two-terminal circuit, can be replaced by a voltage source with a resistance. The voltage can be calculated or measured. You just removing this load resistance and measure the terminal voltage. This is the VTH. And what is the RTH? RTH is nothing but the equivalent resistance throughout this terminal by replacing this voltage source through its internal resistance. These things is written here. You can read out that at any two terminal linear network, this is the linear network because V equals to IR is valid here. Having a number of voltage and current source, there will be current source, no problem. And resistor can be replaced by a simply equivalent circuit constituting a single voltage source in a series with a resistance. So there is a single voltage source with a series resistance, where the value of the voltage source is equal to the open circuit voltage. That is called open circuit voltage because if you open this resistance, this voltage is known as the open circuit voltage across the two terminal network, and the resistor equal to the equivalent resistance measured between two terminal with all energy source replaced by their internal resistance. So I think clear about the Thevenin theorem. Now you can take an example. You try to solve this question, that is the find the Thevenin equivalent circuit for that. You can see there is two terminal, this two terminal, you have two terminal A, B. You have two terminal A and B. Okay, so after there is two terminals, so this can be replaced by a Thevenin resistance with a Thevenin voltage with a Thevenin resistance. This point is A and this point B. RTH and this VTH. Thevenin voltage, Thevenin resistance. Okay, Thevenin resistance, and this is Thevenin voltage. Okay, Thevenin voltage. Sorry, Thevenin resistance, and this is the Thevenin voltage. So you can see here, if we consider the two loop, this is a loop 1 and this is a loop 2. Now for loop 1, you just use the Kirchhoff voltage law KVL, that is the current I1 and this is the resistance. So 3 I1 in there, this is I1 and this is 6. There is no loop current, so there will be only 6 I1 and there is 3 I1. And in this loop, total voltage will be, this is positive and this is negative because this is opposite in the our notation. Okay, so I1 is 0, so there is no current loop in this loop. What about in this loop number 2? This is loop number 1 and this is loop number 2. In loop number 2, you can see 10 I2 equals to 10 because this is along that direction and this is opposite direction. So this become 1. So the voltage across AB will be like that. VTH is nothing but the along that. So 6 I1 into plus 10 I2. I1 is 0, I2 is 1. So this is 10 volts. So across this voltage, this VTH will be 10. And what will be the Thevenin resistance? The equivalent resistance when these are replaced by this 0. So if you take this replace 0, so this is the shortest, so 0 into 10, this will be 0. So 3 plus 3 is 6 parallel, you give 3 and 2 is 5. So equivalent circuit will be Thevenin voltage is 10 volt and Thevenin resistance is 5 ohm. Okay, so this is the Thevenin equivalent circuit. I think clear. If there is any doubt, you must comment in the comment box. Next portion, that is the Norton theorem. So in Thevenin theorem, we learned that any linear network circuit can be replaced by a voltage source with a series resistance. Okay. In the Norton theorem, this state that any linear network circuit can be replaced by a current source with a parallel resistor. Okay. And what will be the current of this current source is nothing but if you replace this load resistance sorted. So this is the sorted current throughout the load is called the Norton current, and the Norton resistance is nothing but the Thevenin resistance. That is the same thing. So when this voltage source replaced by its internal resistance is called the Norton resistance. So this can be replaced by its Norton current with a parallel Norton resistance. Okay, so instead here you can see any two terminal linear network. Linear network means this is the V equals to IR valid here that is resistor with a constant current source, voltage source. Resistor can be replaced by equivalent circuit consist of current source in parallel with resistance. This is the current source, Norton current parallel with the resistor, and the current is the short circuit current between two terminal of the network. This is the short circuit current because there is no resistance. This is shorted. That's why I call this is short circuit current. So this is a short circuit current between two terminal of the network, and the resistance is the equivalent resistance measured between the two terminal. This is the resistance measured from these two terminal is called this Norton resistance, and this is nothing but the Thevenin resistance equivalent. Okay, so Thevenin is called about voltage source with series resistance, Norton called about the current source with parallel resistance. This is the basic difference. The source of the nature will be voltage source, otherwise current source. You will be get the same thing. Now we consider the previous example. If you take this previous example, you need to find out this Norton equivalent circuit of this one. So this must be like that. This is the IN Norton current with the parallel resistance RN, and this is nothing but the Thevenin resistance which is already obtained, that is the 5, that is the 5 ohm. Clear? That is the 5 ohm. So RN is 5 ohm, no problem. You need to find out the IN, that is the Norton current. That is point AB. Okay. So this can be calculated here. You can know, you know that is the Norton current is nothing but the short circuit current. So if you shorted one, you need to find out the current within that loop. Taking three loop. In this first loop, the current will be I1. In the second loop, the current will be I2, and the third loop, this current will be IN, because you need to find out this current IN. So use the Kirchhoff voltage law or KVL in loop 1. You can see 3 into I1 in this resistance. What will be the current flow? This is I1 minus IN. I1 minus IN. And this one I1 also. So 10 minus 10. So you will be get this relation I1 equal to IN by 2. In the loop, sorry. In loop 2 you can see this current here also I2 minus I2, and this is IN in opposite direction. So this is I2 minus IN. 10 I2 minus IN equals to 10. In this loop there is a 10. So this becoming I2 equal to IN plus 1. Now comes into loop 3. Here you can see this is 6 IN minus I1 2 IN, and in this 10 IN minus I2 equal to 0. Put this value of I1 as a IN by 2 and I2 equals to IN plus 1, and then simplify. You will be get IN equals to 2. So you will be get the equivalent circuit like that. Norton current is 2 ampere and the Norton resistance is the 5 ohm, which can be obtained is the similar process. In the similar process, you can be obtain in the similar process like that. So in this similar process, you can find out the Norton resistance also. So clear about the process to find out the Thevenin resistance, Thevenin voltage, Norton current, Norton resistance, and their equivalent circuit. Okay. So if you got this equivalent circuit, after that you can find out easily the current through this terminal or voltage of this terminal, very easy, right? Now comes into the next point, that is the superposition theorem. Okay, superposition theorem. If there is any doubt, you must comment in the comment box, or your suggestion also be put down in the comment box. Next thing is the superposition theorem. What do you mean by superposition theorem? If you have a more than one voltage source in the source, this can be voltage source or the current source, then the individual effects will be added up when they are all are present. Suppose you have a two voltage source, and if you taking these two as a separate out, if you take the voltage source here and if you take only current source here, and if you added these two things, you will be get the same result. Okay, so this state as in any linear network means V equals to IR containing two or more source. This source can be voltage source or the current source. The response of any element is equal to the algebraic sum of the response caused by the individual source. So these are the effect of the individual source. If you added the algebraic sum of these two individual effect, you will be get the combined effect. Okay, while the other source are non-operative. When if you take this source, this is non-operative. When this is to take at this source, this is non-operative. There are ideal voltage source and the ideal current source in the network replaced by the short circuit current and open circuit voltage. So current source is the open circuit voltage and the voltage source taken as a short circuited. Okay. So this is the superposition theorem. If you find out the current flow for this voltage source is I1, for that current source is I2. If you place these two things, the current will be addition of these two individual current. Next portion. Next portion says reciprocity theorem. Reciprocity theorem is says like that if you are network, if you gives a supply voltage here and you will be get the current here. If you take the interchange of these two, if you supply the voltage here, then the current will be the same which we obtain. This is called reciprocity theorem. It states here, you can see, in any linear bilateral network, you know about the bilateral unilateral. At the very beginning we start about the bilateral and unilateral. The bilateral there is the same in all direction. In bilateral you can see is the same in all direction, but unilateral it is different in all different direction. So this is called about the bilateral circuit. This is called about the bilateral circuit. So this is the ball in a bilateral circuit network. If a single voltage source VA is branch A produce a current IB, where is the branch B? This is a branch A. This is a branch A. The current will be VA, and this is the current will be IB. Branch A, and this is the branch B. Branch B. Okay. Now, if you remove the branch A inserted at B, so this is interchange. If this is an interchange, then effect will be also interchange. Produces a current wave in the branch A. The ratio of response of excitation same for the condition mentioned above. This is called reciprocity theorem. The ratio must be same. The ratio VA by VB, and this is VA by IB must be same. Clear? Next portion. This is another important theorem, that is the maximum power transfer theorem. When this is a source, this can be voltage source or current source, and this is the load. This is the load, and this is the source. This is the source, and this is the force. If you take this source and load, if you increasing the load, the power supply from the source will be maximum at a certain point and then decay again. And this power will be maximum when this load is equal to the internal resistance. When the internal resistance equal to the load resistance, then the maximum power supply from this source to load. This is the maximum power transfer theorem. Here written here that maximum power is delivered from a resistive network to a load RL when RL is equal to the internal resistance measured looking back into the terminal of the network. This is known as the maximum power transfer theorem of a linear network. Okay, so the power supply will be increases when this is equal to the internal resistance. This will be maximum and then fall down again. Okay, next thing, and this is proved here. You can see if you take, this is a voltage V, this is a voltage V, supply voltage, and this is the internal resistance R. This is a load resistance. Current through this load. Now the current through this load, what will be the current? Current through this load, if you taking, this is the I. Current is nothing but voltage by total resistance. Voltage is V, total resistance is R plus RL. Now the power is nothing but I square I square R. So I square R. At the maximum power, the first derivative will be 0 and second derivative must be less than 0. Now check. If you take the first derivative with respect to RL, because here the change parameter is load resistance. Here the change parameter is load resistance. So load resistance will be changed. So if you taking the derivative with respect to RL, that is the load resistance, you will be get this thing. Derivative of RL is 1, and taking of this derivative will be gives. Taking the second derivative of this thing, you will be get this one. You will be get this one. For that one, this is the two term here. So first derivative is 0, you will be get R equals to RL, and put this R equals to RL in the second derivative, will be get negative. So these two conditions satisfy. So at R equals to RL, this will be the maximum. So maximum power transfer to the load from the source when the load resistance is equal to the internal resistance of the source of the circuit. Okay, so this is called the maximum power transfer theorem. I think clear. If there is any doubt, you must comment in the comment box. This is the question based on the Thevenin theorem. Superposition theorem and Norton theorem. You try to solve this question. If there is any doubt or any problem to solving this question, you must comment in the comment box. So that's it. This is all about me, and this is my contact detail. You can connect with me with the Telegram channel. This is my online platform, and this is my YouTube channel details. Go to this channel, you will get different series related video, some mathematics also. Like this session, if you learn something from this session, share this video to your friends. Either he or she also get benefit from this video. Subscribe this channel if you new in this channel. Those already subscribed, thanks for subscription. Press the bell icon to get notification of upcoming video. So take care. We'll meet in the next video as soon as possible. Thank you.